Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to be a conceptual video about the behavior of what's called an RC circuit here. So an RC circuit is a DC circuit hooked to a DC voltage source, a resistor, and a capacitor. So let me chat about what we're looking at here. So right here I got a picture of kind of a standard RC circuit. This is going to represent my voltage source, a resistor, and my capacitor here. And I always like to write out, well, what is capacitance? It's charge per unit voltage. Now, when we close the switch on the circuit, right, now we have a closed circuit and we're going to get charge transfer. Charge is going to start marching through the circuit. Now, in reality, what happens are electrons are repelled from this, attracted to this. So reality is electron movement in this direction. However, in physics, the sign convention is assuming positive charge carriers. So our current, as defined by positive charge carriers, is in the direction shown. Now, the capacitor now we know is going to start charging to this polarity. And the charge is going to be growing. So the charge is a function here. The charge is going to be getting higher and higher and higher. Now in my class, and probably every physics class on the planet, everybody does an experiment where you typically keep track of the voltage across the capacitor with time. And you generate graphs typically that have this type of shape over here. Now, usually what you're doing is you're doing voltage graphs. However, I would point out that the charge is proportional to the voltage. So the charge, if you were to plot charge against time, it also has the same type of shape. The charge will hit some maximum value eventually. I call that Q max. And let me talk about this graph here. At first, the current's really high. But after, which is like here on our graph, it starts at a maximum value, which is equal to E over R, and I'll talk about why that is here in just a moment. But once the capacitor gets fully charged, the current goes to zero. So our current graph is looking something like this. Now, some of the initial values here. Let me chat about those. Or maybe not initial values, but let me talk about long-term down the road, the Q max. Eventually, this capacitor will hit its maximum charge, and at that point, the current goes to zero. And once the current is zero, whoops, I forgot the label, E for EMF of the battery. Once the current goes to zero, there's no voltage across here. And now, the equipotential goes right to here. And the voltage across the capacitor is equal to the EMF of the battery. So at that point, the charge is equal to, the charge is its maximum value, and I'll write this right here, and it's equal to whatever that EMF is times the capacitance. All right. The current is a maximum basically the instant the switch is closed, before the capacitor has had time to build up some charge and fight the battery, if you will. And when there's no voltage across this, and you write a loop equation for this, you get E minus IR equals 0. So that's when the current is a maximum, which is why on the graph here I label I max equal to E over R. Now, I talk kind of a little bit more detail here. So in the in-between steps, if we start here and we go around this way and we write a loop equation, that's going to read E minus IR minus Q over C equals 0. The Q over C is coming from here, the voltage on a capacitor. Now, I'm not going to talk about the solution of that equation. This is meant to be a very basic conceptual video here, but that's what's called a differential equation. Both the charge and the current are functions there, and they're related through the derivative. And again, I'll talk about this in another video, the actual solving of equations like this. But for now, I'm just going to skip to this part, all right? This curve right here, you end up with an exponential looking equation that looks like this. The charge is equal to Q max times 1 minus E to the minus T over RC. Again, the math that gets you there is not super important for this discussion. Suffice to say, this function fits and matches well with this curve, right? Now, one thing you'll notice is this term right here. And if you're going to take e to a power, that power needs to be dimensionless. It doesn't make sense to say like e to the 2 seconds or anything like that, which implies that the product RC has units of seconds, and it does, right? The product of R times C is called the time constant for the circuit. And basically, you know what the time constant is it's the time where the charge is equal to Q max times 1 minus e to the minus 1. And what you'll get out of that is 0.67 out of this. So basically, the time constant is the time it takes for the charge to hit 67% of its maximum value. Right? So what is it? It's just a time that reflects how fast the current or the capacitor is charging. If you have a very small time constant, it means that the circuit's charging, or the capacitor is charging very fast. A very large time constant means that that it's charging very slowly. And it depends on both of these, because the higher the resistance, the lower the overall current, and the longer it takes to charge the capacitor up. The higher the capacitance, the more charge it takes to charge the capacitor, and hence the higher the time constant. So just some quick little numbers here. So the charge after one time constant you would get by putting basically 1 RC in here, and you get, Q max times 1 minus e to the minus 1. The charge after 2 time constants would equal Q max times 1 minus e to the minus 2. And if I wanted after 5 time constants, this right here would be, you'd be putting 5 times this here, and you end up with e to the minus 5th here, and so forth. So that's what the time constant is. It's just a number that reflects how fast or how long it's going to take the capacitor to charge up. Again, the mathematics involved from here to here, I'll save for another video. It's not super hard math, but this was just meant to be a conceptual video about RC circuits and their behavior. I hope that this has helped. Have a great day.